We're going to begin discussing about the basic structure of an atom. As you may recall, there are three different subatomic particles to an atom: the electron, the proton, and the neutron. How the structure of the atom works is the protons and neutrons are located in the center of the atom, which we refer to as the nucleus. Then the electrons orbit around the nucleus. We're going to be talking more in depth about how this structure is scaled and how this works, but that's your basic premise. And in fact, something that's not usually discussed is the scale of the nucleus to the electrons. So to be clear here, this is 1 femtometer, okay? 1 angstrom is equal to 100,000 femtometers. So this line is representing an angstrom. And if you see, a helium nucleus is about 1 femtometer. So that is 100,000 times smaller than this line. If you notice, roughly the radius of this atom is an angstrom, which means that the nucleus is 100,000 times smaller than the actual radius and the actual size of the atom. I once watched a lecture that described the nucleus of an atom being like the eraser on a pencil. That's a terrible eraser. And the electrons orbiting on the roof of a building. So that small as an eraser and that large of a distance to the electrons orbiting. So just to give you an idea, usually this is what pops up into our heads, at least that's what pops into mine, but the distance between these is far greater than what's usually discussed. Here's what you need to know about the varying subatomic particles. The first thing that you should know is that protons are positively charged. You should know neutrons have a neutral charge and that electrons have a negative charge. In addition to this, you should know that protons and neutrons are located within the nucleus and that electrons orbit the nucleus. And then the last thing you need to know is that protons and neutrons have mass, where the mass of an electron is negligible. What I mean by that is this. Electrons have mass, but their mass is so much smaller in compared to the mass of protons and neutrons. Generally, when we're discussing about atomic mass or the mass of an atom, we generally disregard the mass of those electrons. Not because they don't have mass, but because their mass is so much smaller in comparison. The next thing you need to know are some identifying factors that can be found on the periodic table. So on the periodic table, which you can find for every element, is first just the atomic symbol, so the letters that represent that element, and the element's name. In addition to those two things, there are two numbers that tell you different information. So the first number is like the whole number that is written on every element. Hydrogen is starting with 1 and then working your way down. This is called the atomic number. And this number is always equivalent to the number of protons within an atom. This is actually the identifying factor of every single atom. So if you were to look at an atom and see that it had 15 protons, that means it is a phosphorus atom. If it had 32 protons, it would be germanium. So the amount of protons actually defines an atom and therefore defines an element. And this atomic number is always the same thing. The other number that you can find is referred to as the atomic mass. And actually a better word for this is average atomic mass. We'll be discussing later why we use the word average for this. At this time, I like to point out the difference between two words that we use when we're discussing the periodic table, which is atomic mass and mass number. So atomic mass, as you can see, is that number that is found on the periodic table. And it is a calculated average. We're actually going to be doing those calculations later. Mass number, on the other hand, is not found on the periodic table. And it is actually the sum of the protons and the neutrons within an atom. So the reason that we have atomic mass and mass number is basically the mass number is communicating basically the mass of one solitary atom, and the atomic mass is communicating the average mass of a large group of atoms. Considering we generally work with atoms in large groups because atoms are ridiculously tiny, average atomic mass is the number that we use most often, where mass number is communicating the mass of one solitary atom. One thing you're going to have to be able to do throughout this unit is identify the number of protons, neutrons, electrons within an atom. So our most basic is hydrogen. Its atomic number is 1. It's the first element on the periodic table, which means the number of protons it has is 1. These two numbers always equal each other. I want to point out the letter Z here really quickly. Sometimes the number of protons is hyphenated, or sorry, not hyphenated, is replaced by the letter Z. That will become important later on in this unit. So sometimes we just refer to as the number of protons as a letter Z. If an atom is neutral, meaning it does not have a charge, because protons are positive and electrons are negative, in a neutral element, the protons and the electrons also match. 1 proton, 1 neutron. If you know nothing different, it is safe to assume protons and neutrons equal each other. They don't always equal each other, and that's something we're going to be talking about later on here as well. Mass number, if you recall, is the protons plus the neutrons. So in this case, it would be 2. And atomic mass is that number on the periodic table. So to the 100th place for hydrogen is 1.01. Oxygen, real quick, atomic number is 8. So the protons are 8. If it's neutral, the electrons are 8. If you know nothing different, assume neutrons are the same, so 8. Mass number is 16. Atomic mass would be 16.00. Here are the other values filled in case you were wondering. One of the first topics we're going to discuss here is isotopes. Like previously mentioned, if you are not given any other piece of information, it's safe to assume protons and neutrons equal. In fact, though, for many atoms, this is not the case. So isotopes are one way to help define that. Isotopes are defined as the same element with a different number of neutrons. So for example, down below I have 3 isotopes of hydrogen. You can tell that they're hydrogen because they all have 1 proton, and atoms are identified based on the number of protons they have. These are isotopes of each other because they have varying numbers of neutrons. So this one has none, this one has 1, and this one has 2. So I kind of like to think about this as different models of the same car. If you also recall, protons and neutrons have mass. So this would be the higher mass isotope, where this would be the lower mass isotope. And basically what happens is, and we're going to be doing this here in just a moment, we calculate the average atomic mass of all of these isotopes. So all 3 of these isotopes of hydrogen exist. They're out there in the world. So some hydrogen is just 0 neutrons, some's 1 and some's 2. And some of these are actually more common than the other. And how common they are dictates that average atomic mass. One way to communicate if something is an isotope or not is by writing it out in isotopic notation. Over here you can kind of see the formula that we use for this. So for our example, we're going to use carbon with 7 neutrons. So to start off, you just start off with the chemical symbol. So for carbon, that would be a C. In the bottom left number, we write down how many protons that element has. So for carbon, it's 6. Again, notice the letter Z here for protons. And then in the top left corner, we write the mass number, which is protons plus neutrons. So if this has 6 protons and 7 neutrons, the mass number would be 13. That's one way to communicate if something is an isotope or if it has different numbers of neutrons. Another way is referred to as hyphen notation. It is simply the name of the element, so carbon hyphen 13. That 13 being the mass number. So either way, the mass number has to be communicated, and remember that mass number is equal to the protons plus the neutrons. Let's practice filling out a similar table as before, but now with isotopes. So the first one we have here is Au, which is gold. So the atomic number for gold is 79. Had to look at my periodic table here. It's that whole number. So the protons is 79. Remember, these are always the same. Number of electrons. There's nothing in this notation communicating a charge to me, no positive or negative, so I assume it is neutral. So therefore, for there's 79 protons, 79 electrons. Now the neutrons is where it changes up. If you remember, the number in the top left is the mass number. So my mass number for this is 197. Mass number is protons plus neutrons. So for neutrons, 197 minus 79 is 118. So that would be my answer for the neutrons. The atomic mass, remember you get this from looking at the periodic table. For gold, I am seeing 196.97. Let's do it again for bromine. Bromine has an atomic number of 35, which means 35 protons. Again, nothing positive, negative here, so 35 electrons. This is the hyphen notation now, so that dash 80 means the mass number is 80. So to figure out neutrons, I'd take 80 minus 35 for 45 neutrons, and the atomic mass of bromine is 79.91. Here are the other values in case you wanted to practice. The next thing we're going to cover is how the average atomic mass is actually calculated. So like I mentioned, there are different isotopes of different elements. So for example, carbon has a few different isotopes. There is carbon 11, carbon 12, carbon 13, and carbon 14. All of these occur naturally within nature. So basically, the purpose of the average atomic mass is this. If I'm working with a really large amount of atoms, which again, in most cases you are, because atoms are so small, and if I wanted to move forward and do a chemical reaction with carbon, I would need to know on average the mass of just one atom. So to do this, we calculate an average. So if I've got 11, 12, 13, 14, math, if I figure out the average, it would be 12.5, right? That's right in the middle. Well, look at the periodic table. The average atomic mass of copper is actually 12.01. So why isn't it the middle? We also have to factor in how prevalent these isotopes are. Another way to say this is the relative abundance. Relatively, how abundant are these isotopes? What if when I told you these were the isotopes of carbon, I also told you that 98.9% of all carbon is carbon-12? Well, if most of the carbon is carbon-12, that would probably skew the average closer to 12, which it does. So the more prevalent an isotope is in nature, the more hold it's going to have on the average. So we need to not only factor in the different isotopes, but also the relative abundance of that isotope. So let's look at an example for copper. Copper has two common isotopes, copper-63 and copper-65. Again, copper-65 would be the same atom of copper, but with two extra neutrons. These are isotopes of each other. Same element, different number of neutrons. The relative abundance is as follows. About 69% of copper is copper-63 and about 30 is copper-65. So what I would do before making any of these calculations is guess. So based on these numbers, I think my final answer is going to be closer to copper-63. Let's try. Here's what we do. We take the mass multiplied by the relative abundance. So the mass being the mass number. So I'm going to take a mass number of 63, and I'm going to multiply that by the relative abundance. In order to do this, you need to convert the percentage into decimal notation. So 0.6910. And I'm going to add that to the other isotope. So that mass is 65 multiplied by decimal notation 0.3090. So once you've got this written out and you calculate your final answer, you should get 63.618. Now, we did a calculation, so we are going to have to check our sig figs. So here's the thing. The two mass numbers are actually exact values, since these are the sum of the protons plus the neutrons. So those are almost countable, if you want to think about it that way. So you could count out the protons and the neutrons. So these values are exact, so we will not consider those at all for sig figs. So then what we're going to look to is the percentages. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So 63.62. And our unit here is AMU, atomic mass units. So if you recall, we had predicted that our atomic mass would be closer to copper 63, which it is. So the fact that copper 63 is more abundant, that causes our average to be closer to 63. If you want to pause the video and try this one on your own, in just a sec here, I'll have the results. So without sig figs, you should get an answer of 237.9783. Again, our average atomic mass is close to our highest relative abundance isotope. The next thing we're going to discuss is ions. So ions are defined as atoms where the number of electrons do not equal the number of protons, which results in a charged atom. So you can have one of two kinds of ions. You can have a cation or you can have an anion. Cations are when electrons are lost, resulting in a positive charge. So since electrons are negative, if you lose negative electrons, there will be more protons causing a positive charge. Anions are when electrons are gained by an atom, resulting in a negative charge. Because electrons are negative, if you've got more electrons, it has a negative charge. So for example, this would be your cation, and this would be your anion. So how this works is hydrogen generally has one proton, so if it has a +1 charge, then it would have 0 electrons. Nitrogen generally has 7 protons, but with a -3 charge, that means it has 3 extra electrons, so it has 10. One way you can always remember this is cations are positive. Sorry. So we can fill in one of these tables now with ions rather than isotopes. So we've got chlorine here. Chlorine's atomic number is 17, so it's got 17 protons, always and forever the same. Atomic number equals protons. For electrons now, since this has a charge of -1, that means there's 1 extra electron, so that means there would be 18 electrons in this case. Again, if you're not told otherwise, just assume protons and neutrons equal. So the mass number here would be 34, and the atomic mass can be found on the periodic table as 34.45. Again, that's that calculated average we were doing before. Magnesium, atomic number of 12, therefore 12 protons. This one has a +2 charge. So since it's +2, that means it's missing 2 electrons, resulting in a charge of 10. Assume, same for neutrons, 24, and then the average atomic mass according to the periodic table is 24.31. Here's some additional examples if you needed the extra practice. That is it for the basics between protons, neutrons, and electrons, and isotopes and ions.